Okay, so in the last video we looked at this idea of the atom being made up of smaller particles and a central nucleus with nucleons inside of protons and neutrons with electrons on the outside. You can get hydrogen as H11, H21 and H31, okay? And their names would be protium, deuterium and tritium. Now these are all still the same element. They're isotopes of the same element because they've still only got one proton and therefore one electron that's going to interact with other elements, okay, other atoms. The difference here is this one has to have a total of one nucleon here, the mass number is 1. So we only have to have one nucleon, it's already got that, so we can leave it alone, no neutrons. This one here has to have a total of 2, we need 2 nucleons inside, so we need a second nucleon drawn inside there, the neutron. So the nucleus is what that is made up of that. The third one here, 3 take away 1, we need 2 neutrons inside there to actually show a total there of 3 in the nucleon number. So that's the basics there. The issue we've got with the nucleus at the moment is when you've got larger nuclei there, you've got lots and lots of protons in there that are positive. And they're going to all try and repel each other and push each other away. So these are going to be pushed out by all the other protons here pushing on it. That one's going to push it this way, this one's going to push it that way, that's going to push it this way. They're all trying to push each other out away from the nucleus. So why doesn't it fly apart? The neutron proposed by Rutherford would have actually sort of been an idea of as acting as a glue or sticking as a glue. But this is a really large force we're talking about when you add them together and give you the total repulsive force. Okay? So it was proposed that there was a strong force actually holding these together that acted between the nucleons, a strong force. And because it was in the nucleus, they called it the nuclear force. Okay? So the nuclear force has some key properties here. So let's have a look at this strong force. Quick recap. Just be aware that the discovery by Thomson of the electron, okay, which is a small negative particle, led to subatomic particle discussions. The alpha particle scattering experiments done by Rutherford, Geiger and Marsden led to this idea of the typical one you might have been used to, central nucleus which was positive, electrons going around the outside with a lot of empty space. The new things we've introduced here are the idea that the nucleus contains nucleons, which are your protons and your neutrons here. The idea we've introduced is the composition of the nucleus is it's made up of protons and neutrons, neutral particles. They're the nucleons. They sit in the middle. And you can get isotopes of that which have the same atomic number here but different mass numbers because we've got different number of neutrons in there. Okay? So, what holds it all together when you get some large repulsions there? So the nuclear force, what are its key properties there to try and actually sort of overcome that vector sum of repulsion? So, key things to be aware of with the nuclear force. First of all, it's short range. It only works over small distances, so you can call it a short range force. Now, how close is that? We're talking about just the distance between the nucleons here. It doesn't actually work between one nucleon and one too further over. It's just too far apart by a small amount. So it is a short range force. Think about it acting over neighbouring nucleons that are near each other, okay, right next to each other there. So not much further than that. It's a very strong and attractive force under those conditions where it's fairly close. If it gets too far away, it goes down to 0 very quickly. Something to be aware of as well though, if it gets really, really close, almost touching, it becomes repulsive. So actually pushing each other away by the nuclear force. Okay? But this force between neighbouring nucleons is enough under most circumstances to hold it against the electrostatic repulsion. So it's a very strong force over short range. Very close ranges, it's repulsive. It is independent of the charge. Now what does that mean? So if it's independent, it means it doesn't actually sort of affect it. So the charge does not affect the nuclear force. In other words, if you were to put a proton and a neutron near each other, the nuclear force of attraction would be the same as if you put 2 protons near each other or 2 neutrons near each other. Because these are all equal forces, okay? So it is not dependent on charge at all. Those forces are all equal, okay? So they're the key things to bear in mind about your nuclear force. Now it's just worth a quick look at the graph of the nuclear force here. So the nuclear force, the strong force here, is shown by that blue line there, okay? And you can see it's attractive here in that area there in terms of distance, okay? And this is a separation of 10 to the minus 15 metres, but I've put some nucleons in there to give you an idea of the scale, okay? So it's attractive when it's at certain distances away. And the optimum distance here is here. That's your best separation from there to there. That's your optimum separation where the nuclear force is working the best. And you can see it's actually stronger than the electrostatic force here in red and overcomes that and manages to hold it together. Okay? What you can also see from this graph though is that at really close distances, if you were to try and move this from here to there, it would be repulsive. Okay? So it's very repulsive at really close range, and it's strongly repulsive. That continues on to a really high peak there. Alright? The other thing you can bear in mind here then is if you actually see that as the optimum distance, the next nucleon over would actually be outside the range of the nuclear force here. You can see it drops off to virtually zero there. So it is only the neighbouring nucleons that are going to experience that nuclear force, not the next one over. These two will not exert a nuclear force on each other. This pair will, and that pair will, but not non-neighbouring nucleons.